So it's now recording. Confirmation. Okay, so Usama, please. Do you want to come here? Or...
Yeah, I think it would be. Do they have a trigger to move forward, or do we have some trigger to move forward, or? I don't think we have. Okay, then,
I will do the.
just one comment. Gideon is the only one that is remote right now,
Yes.
right? So if you have any problems listening, just let us know, because we had some issues with the alls before. So maybe you need to speak a little bit louder to someone. Yeah, so they can capture the sound, but if you have any problems, speak us or say something.
How do you do that? Slide, image.
Can I just clarify for the purposes of note taking? So all of the slides are going to be shared afterwards anyway. So
Yes.
I don't need to just note take the content of the slides. Right?
Absolutely
There
not.
will be no value to that. Right. Okay.
In the Zoom, you don't have that window.
All right, you share. All the desktop. Yeah, do you see the presentation on screen?
Yeah. Yeah. All good.
Awesome. Great. So welcome everyone and thanks for being here. So what we have is trying to cover an overview of Attested TLS and to be aligned on what this is all about. Okay, next please. So we typically start with TLS protocol in the past, and then we talk about attestation and then somehow merge the two things together. So this time we are going to do the reverse, which is namely starting with attestation, providing a wider overview, and then going towards attestation as being used in this protocol. So the idea is that attestation, as I have written, so this is a work in progress. We have done some research on this, and so the thing is not yet final. So it's still there is some room for discussion and so on, and a lot of research here. This is one of the definitions which is from NIST, which defines what attestation is: the process of providing a digital signature for a set of measurements. There are some terms in red which I will describe, which are important: securely stored in hardware, and then having the requester validate the signature and the set of measurements. So three important terms. The first one, digital signature over the set of measurements, and the third one, the requester or any other company will then validate the signature and the set of measurements. So what this actually means is, in my understanding, basically we have some kind of measurements, and then some entities doing some signatures which should be trusted, because then this acts as the trust base or the TCP, and then the other entity can then validate the signature and these measurements. So it needs some reference values of these measurements, like what are the golden values of these measurements. Next please. So unfortunately, the NIST glossary actually attributes this wrongly to this special publication. However, it does not belong here. This publication clearly states that we are reproducing the definitions from this, so this actually belongs there. But anyway, the important point here to note is, next please. The important point here to note is that it's not necessarily a digital signature. It can be done using other ways in cryptography. For example, MAC, if you have a shared key, so you can actually do MAC, which is much more performant than digital signatures, and you don't need to go into the asymmetric crypto. And that's one thing. Next, please. The set of measurements is not also the only thing which attestation does. It necessarily also needs, for instance, nonce in order to ensure that it's accurate. So the definitions which exist as of now are actually incomplete, inaccurate, and so on. There is a wide scope of a lot of improvement. Next, please. So as I said, we will start with attestation, go towards attested TLS. So this is the overall spectrum of attestation. What we have done is to categorize it into two main high-level categories. Secure channel establishment is one of the applications or use cases of attestation, and the other one is credential issuance. Secure channel establishment, as the name says, two or more parties are actually trying to create a secure channel through which they can transmit the data. What secure channel means is, I will skip for the moment, like it could have again different meanings. It could be a confidential, data integrity protected, or in other sense. But there are various protocols which I have also classified, like this IETF, DMTF, two standardization bodies. For example, the Attested TLS, which we will come into throughout the day. This is that thing. Ad hoc, basically the author is also here with us, so she's trying to standardize this attestation over ad hoc. SPDM already includes and is a standard, already includes attestation. And among the custom ones, which are non-standard, Google ECAP is one of the protocols which uses this for attestation. On the other hand, credential issuance is that some requester requests something and provides its evidence as part of its authentication. And the other party, which is namely the issuer, identity issuer, can then issue some kind of credential. And this credential can be either a certificate or an authorization token at a very high level, so this classification. And the format of the certificate is typically in X509. And the authorization token is typically in JOT format. And in this category, we have a number of protocols like CMP, ESP, ACME, which are here listed. And on the other side, or from the IETF, on the other side for authorization token or auths, very famous protocol. And the COCO KBS broker service is the other part, which is non-standard or the custom one. So this gives overall an overview of the ways in which we use or the protocols are actually using attestation. Next, please. So it's not only simple protocols which are actually using attestation, but also whole computing paradigms. Trusted computing based on TPMs has attestation as a core part of its protocol. So, and similarly, the attestation research has been become alive again because of this confidential computing, where attestation is the key enabler of confidential computing. And it can be of two types. Both of them have attestation as a key component, even if it's done on the CPU fully, or even if you have a GPU for the acceleration. In that case, also between them, you need attestation, like a composite attester as in the RATS architecture. But we will come to that next, please. So this is the overall history for both of these domains, how attestation has evolved, starting from the research, which was in 1989, the DD SSA paper, and then first industry consortium formed in the 1999, which transformed into TCG, and then again research started on the privacy perspectives, the DA direct anonymous attestation, and TPM 1.2 and 2.0 standardized in 2009-14. And then from here starts the confidential computing era, which is the Intel SGX, AMD, and so on, which have again given life to the attestation research. And also in that, here the things got into implementation. The Riot paper actually does the implementation, which was proposed back in 1989. And also it continues, like IDF RATS working group was formed, and then started some. Now we see an era of the VM-based trusted execution environments like AMD, SAP, SMP, Intel TDX, ARM CCA, and also the attestation SIG was formed, which is completely focusing on the attestation side of the thing. And also the RATS architecture was standardized in 2023, and the CPU, GPU accelerated confidential computing, which I described on the previous slide, then also came by NVIDIA in 2023. And finally, the RATS EAT format, which is going to be standardized this year, hopefully, I think. And the collaboration model here, so overall idea of the whole thing is that we have specifications. One team, or let's say some people working on the specification, which is the, let's say, the IETF drafts formulating all the protocols or the things, how they work. And then one team which is actually taking that specification and building something on top of that, that's the coding part for the actual implementation. And on the other side, for instance, in the TLS working group, there has been a consensus and actually that any extension of the TLS would go through a formal verification, any non-trivial. So of course, for trivial extensions, we don't need it, but for non-trivial extensions of TLS, we need to maintain all the work that the formal community has done. And in order to uphold all these properties which are there for TLS, they should uphold also for each and every extension of TLS. So that's the main idea for this. That and then the back loops that you see is that, for instance, something is missing in the specification, the formal verification team would give an idea that, hey, this is missing, so this needs to be incorporated within the specification. Something is missing in implementation or something like that, so this will come as a feedback to the specification team that this needs to be done. And similar happens for the deployment when things mature, so the implementation will go into the real life, and then we will see the things happening in the real life, and then there might be something missing which the implementation then needs to take care of, some attacks and so on. So that's all the things that happen. So the point that we want to make here is that each of them have to collaborate as early as possible. Formal verification team, for instance, should be incorporated into the design as early as possible. There is a lot of effort involved early in the process that you have to go through all these things, and lesser reward for the researchers because then you cannot publish papers on this. But anyway, the ideal model is that when we start with specifications, soon after that, the formal verification team should be involved. And similarly for implementation, early involvement will lead to a better kind of collaboration model. So that's our main aim. And that's why we are here to discuss it further today to see what's missing and what needs to be done in order to have better results. Next, please. Okay, so that one of the standards IETF talks about this RADS architecture, which is one way of visualizing how the definition that I showed previously, how it all happens. So the RADS architecture defines three main roles, which is the attester, verifier, and the relying party. And how they work is that the attester provides an evidence, and the verifier has access to these endorsements by which it can confirm its identity. And the golden values that I talked about, or the set of measurements which misdefined, it needs the golden values to compare that, which are here called as the reference values, and the entity providing that is the reference value provider. And then it could have additional policies in order to check that everything is satisfied, whatever it needs in order to do that. So that's basically the verifier owner providing that policy for this part. And then once the verifier, what the verifier produces is this attestation result. And now the relying party, which is the end, which can be the end entity, can now make a decision based on its own additional appraisal policy. So this is how the RADS architecture, in a nutshell, is basically defining this. And there is a RADS working group. Next slide, please. I think we have this nice RADS thing, which is basically defining all of these and trying to standardize different parts of all of this thing. And next, please. I think I have one final. Yeah. So all the protocols that I mentioned basically are trying to incorporate this attestation. And I think that's it. And then I would like to invite panelists to continue about the attested TLS part.
Cool, thanks, Susan. So what is this thing that we're trying to do here is an extension to the TLS handshake protocol that allows the two peers to authenticate to each other using stronger authentication primitives, attestation evidence or attestation results. And this is, this is a bit of is going in a slightly different direction that normal TLS, where you're using typically your static long-term credentials in order to identify the endpoints. Where we add on top of that, because we're not dropping all of that. We're just augmenting that kind of identification that is name-based, let's say, to an authentication that also includes peer runtime status, right? So security metrics coming from the peer, maybe both peers, because we want to allow mutual authentication. So yeah, in a nutshell, the idea is to introduce these protocol extensions to the 1.3 handshake. So and we are 1.3 only. We're not backporting it to 1.2 in no ways. That enables binding the authentication key is using the handshake to a remote attestation session. So we want to basically plug the two mechanisms together in order to, as I said already, augment the authentication strength. So why we need that? Because well, because we need it, but PKI and is good for conveying the network identity of a service. So PKI is great because it binds a key pair to some sort of domain name, right? So an identity of that peer on the internet. Remote attestation is good at doing something else, which is conveying the security state of the device, and so decide whether the execution environment where the actual keys exist is trustworthy. And the idea here is to take these two worlds and combine them together efficiently to get security benefits of both. And so the core change is here to enable remote attestation conceptual messages, in particular evidence and attestation results, to become first-class credentials in the TLS and shake, similar to what the X509 certificates are, and also PSKs with the identity units. And to do that in a way that accommodates the variety of different formats that we see deployed in the wild in terms of the evidence formats, especially, right? So we have attestation coming from TPMs, from confidential computing environments, all different. You have a real zoo of formats here that we need to accommodate, and we want to accommodate them by making the packaging of the actual conceptual message generic. We think that this approach has benefits, of course. One is better security in the sense that we, as I said, we augment the authentication primitives with attestation, and therefore we provide more granular, more interesting, in fact, security metrics that can be evaluated by the peer in terms of their access policies and whatnot. And also we think it's going to be better performance in terms that especially in terms of latency reductions, because the channel establishment and the remote attestation are bundled together, and so you don't waste flights. Like for example, if you wanted to have attestation on top of the TLS handshake, and therefore have further back and forth for the peers. So everything is collapsed into the 3 flights of the TLS 1.3 handshake, and that's good. So this is sort of where we are at the moment in terms of extensions. So we have client hello, that is the ATLS extensions that allow negotiating the capabilities and also exchanging information about, say, for example, freshness indicators and the type of supported credentials, etc. We extend the second flight, so back from the server to the client, with again the other hand of the negotiation, as well as the extension in the certificate message that allow transporting attestation conception messages. Third flight, again, if mutual authentication is requested, then you have an extension certificate message that allow carrying alongside the certificate any attestation message that has been negotiated upfront. And then at the end of that, you have the security channel established, hopefully, with attestation as well. We started with these two use cases. One was IoT related, so device onboarding, and the other one was confidentiality related. So we have this cloud workload that needs to identify itself securely to someone, let's say, for example, a bit of IP, right? For example, an MN model or whatever. Or, for example, a key broker, like in the Coco use case, where you need to tell someone who you are and where you're executing before that someone can release the keys that allow you to unlock the workload that was sealed cryptographically. But we have more use cases. For example, I hope I understood from Ginny and Andre that you're going to talk about mobile network use cases as well. And also very interesting, yeah. But we started with this, so this was just the beginning of the fun and the motivation. We have a prototype at the moment, which is hosted at the CCC attestation SIG and the Attested TLS POC repo. There, this is a pretty chunky integration of different things here. We have parsec abstracting the root of trust. We have a TPM attester at the bottom. We have embedded TLS endpoints that can do mutual authentication using mutual TLS using attestation credentials. And we have on the back of that a version verifier that takes care of various things, right? Of course, verifying the attestation evidence, but also because this is a platform attestation plus key attestation protocol, it also do some magic in order to release the key that has been attested. There's a Docker containerized situation there. It can run pretty easily if you want to. Yeah, we plan to keep this alive and to evolve it as we go, because it's a good way to explain all the pieces and how they fit together in order to have the end-to-end realized. Here's a bunch of links which are maybe not interesting in this content, but they're there so that if you want to click on the slides, and you will find what we have. So the draft itself, another draft that explains how to bundle platform attestation and key attestation. The CMW is another piece of standardization that we're putting forward in order to realize that kind of conceptual message agnostic formatting for the back and forth, and then parsec, reason, and TLS. For now, we were having these partners on board, but we hope we'll extend with more. We have a Slack channel with on the IETF Slack instance, and we have this bi-weekly meeting on Monday and Thursday to accommodate various people from different time zones at 4 p.m. CET. There's a Zoom meeting link there. So yes, this is the place where we are working, mainly the Rust working group, the CC attestation, SIG, UFMRG in the RTF, and IETF itself, of course, taking advantage of the active space that they give every meeting to try and get together and move the work forward. That's it from my side. If you have any question? Which were the right? Then we should move to. Hello. Welcome. Eugene and Andre.
Yeah.
And stop share and then you will take over, right?
Yeah. What's the audio from? What's the audio coming from St. George? Yeah, that's coming from.
Yeah.
In theory, it can capture the audio of the whole room, so no matter where you are.
So just to check, Guillaume, did you hear properly?
Yeah, not exactly. It's a bit noisy.
Yeah,
I think the sound is okay. They're just several people talking. I think that's why.
Allow this screen sharing on my computer, which means that I need to restart the.
Should be capturing the sound again.
Yeah, okay, so I'm Jimmy Tom from Ericsson Research in Finland, and Grace Smith from also from Ericsson Research, but from Sweden. And we have been doing some work around attestation, especially in kind of a particular use case, this computational offloading for mobile devices. And we'll just come back to that in a second, what that means and what kind of requirements we can have in that context. So this so-called dynamic computational offloading is basically an idea of a service that we would provide, for example, in 6G networks, so that the devices can offload some computing, like from the device itself into the network. For example, if we, in some cases, can make sense to utilize like resources in its edge computing environments, if we have like more computing power available or more powerful GPUs, or if we in general need to save power like on the device itself, by then if it's some very computationally intensive task and we don't necessarily have a lot of networking between the device side and the edge side, and we do a lot of computing on the edge side, and it can make sense to do offloading some computing from the device to this edge environment, which we have the network. And so we have like developed a framework for enabling this, and there was like some components, like of course we have like some execution environment for running things on the device side, and then also when we run it on the edge side, and then something which is called elastic channels that then enable this like networking between the parts that we still have, like some part of an application running on, let's say, a mobile phone or an IoT device, and then some part of it can be executed in the edge environment, and then we have some communication between those. So this is meant to be like a dynamic in the sense that we can, like on demand, we have something running on the device, and some part of it is uploaded into the network. If we doesn't need to be or can't be running the network anymore, then it can be also put back onto the device. So we can like flexibly move computation from the device to the edge environment or back, or place it as we like. So it's not this kind of a more maybe traditional thing that you have like a very static service in the cloud somewhere, which where you get computational resources, but it's more that you can actually move but even something like which is based on the same code, you run it on the device or at the edge, and then you move it up to between the two. So we have this system defined. We're going that much into details here, but again, we have this like the device side, and then we have some components there which are handy. For example, is that when should something be offloaded? Is it something that updated devices like a battery level is low, and that's why we need to move some computation to the edge or something something similar. And then there is like a handler which is taking care of then taking some part of the application and migrating it to the is like a sort of offloading cluster, which is usually in this case located at somewhere in the mobile network. And then it is on this offloading cluster side, we also have like some of these control plane components, which are like taking care of this, that allocating resources for its execution if needed and so forth. And then we have there also is some kind of a host or execution environment, which is then executing the offloaded code. And also there we have like some handler, which is handling the receiving this module from the device side and to execute it in this host. Well, that's the one technical detail. So we are running these as WebAssembly module instances in this offloading cluster, and that's gives a good portability and some boxing properties and so forth. So. But some of the requirements can be highlighted here. So we want this to be like a platform independent solution, not depending on any it's like a specific CPU architectures or things like this. And we also want the solution overall to be very lightweight and performant, so that these like offloading operations can be triggered very quickly and the offloading can happen very fast. Also, the recall should be able to happen very fast. And well, we want low performance overhead in general. Of course, we want to be able to use things like GPUs or accelerators on these offloading codes and so forth. So the performance aspect is a pretty important one here. Well, obviously, this solution needs to be secure overall, and come back a bit to that in just one slide. And then, well, this polyglot simply also means that we want to be able to support applications written in different program languages. Again, we're not typing a specific language, and that's one reason also why we use WebAssembly, so that we can compile from any languages and create these modules and execute them like a common runtime. So then we get a bit more to this specific of this network integration number one. One thing is, okay, so we plan to potentially offer this as a mobile network integrated service. And one thing that the network can provide is this authentication, basically sort of authentication action of both sides, so that a device that wants to use an offloading service should of course be authenticated to that service, but then of course also the device has an interest to know that the offloading service is or an authentic offloading service that it can trust. And in this 3GPP standards for 5G, there is something we call authentication and key management for applications, which means that well, the device is anyway authenticated to the network, which is SIM credentials, and then we can reuse these authentication mechanisms to provision a pre-shared key both on the device side, well, user equipment in this 3GPP terms, and this shared key also to this so-called application function at the edge side. And that means that then when we establish, for example, the TLS connections between this like device side and the edge side, then we want to be able to use these pre-shared keys in this connection. But TLS supports that, and it's worked for a long time. Then we also want to combine that with attestation, but we'll get back to that in just a minute. And yeah, as mentioned, since these services would be then typically provided in an edge computing environment where we can hopefully have like low latency between the device and the computing environment. often a requirement for these uploadable applications. And this is also, since this is of course the devices can be mobile, so it means that they can perhaps move, of course, from one location to another. They may need to you have uploaded already something to one edge environment. They might need to switch to using another edge environment, and we need to migrate the uploaded module to another edge environment. And this can be like a quite dynamic setting also, that we are opening connections between like the device and edge sites, but not maybe quite frequently, but that's anyway something that can happen. So it's not again, not a static setting that we only like open once a connection and then we can keep using that. And so. Then the next thing here that we want the this execution environment where we are executing these offloaded modules or tasks on the device, that should of course be protecting the workload and the data we process. So we have been working around this, that the offloading host or the execution environment on the host at least runs the DEE, so we can protect it like from the for example, the administrator of the host and so forth. So I mean, the standard confidential computing use case in that sense. But that also makes sense since we are running this DE, and when we also need to attest it to the device side. So the device side, I mean, obviously again, this is very standard confidential computing thing that we need to attest that we know what is running in this offload service environment. And this is, we preferably would want to attest the whole thing running there. So not just, for example, something like which is managing the connections keys or something like this, but actually the whole thing which is executed and which is running these tasks and handling the user's data. So it's like attestation of the full hardware or software stack which we have there on the edge and providing this calling services. We also want to be able to have mutual attestation if needed, so that also the device side can maybe to attest itself. So we are interested also in this mutual attestation case. And one thing is also that we want to be able to use multiple types of DEEs in a broad sense. So it's like DEEs from different vendors or DEEs based on process based or based. And also, of course, if we have accelerators, we want to use this like be able to do constant attestation and so forth. And we would want to do it with like some common mechanisms and abstractions, like very specific solutions for each type of DEE or vendor or setting. So yeah, these standard abstractions are interesting to us. And just one thing to note again here, that it can be again quite a dynamic thing. These execution environments might be possibly spawned on demand, so that we're not like spending computational resources or having unnecessary state at the edge if a user is not doing offloading. But at the time when the user wants to initiate offloading, then that should be able to we need to allocate all the resources for it. But nonetheless, we want it to happen very fast and as few milliseconds as possible. So we want to be able to spawn these instances on demand as well. So it means that, for example, well, this offloading host environment, it can be something like even like a large confidential VM or something like that. But then, of course, booting something like that can take quite long. Or it could be something more lightweight, like something like or something similar, which might be then quicker to spin up. That's not really architecturally, shouldn't really make a difference, like how big these instances are, but the more lightweight, the better actually this things performance and resource consumption. Yeah, this is just also illustrating, of course, WebAssembly can provide us with this like sort of so-called two-way sandboxing. Of course, if we have like a WebAssembly sandbox in the DE, but we also have the protection from the itself. So it's from protocol point of view, that's relevant. So yeah, then we get to this attested TLS, as mentioned. Of course, we want to be able to use these kind of standard protocols and abstractions. And well, TLS, of course, is what we normally use for connections. And then as also mentioned, that we wanted to be able to use it with these pre-shared keys together, then with this attestation. And we want this the handshake to be as quick as possible, so in as few milliseconds and round trips as possible. Basically, we don't have very strict numbers, but just as an example, that if the handshake overall takes only like let's say a few milliseconds, but then we add this like I don't know evidence generation or verification or something, and that starts to take like tens or hundreds of milliseconds, then we kind of have ruined performance, and especially if we do something like let's say mutual attestation, and that has to be done like serially, so that we first have for the client attest and server, we can't like parallelize anything, then of course we get like the performance will be twice maybe. So yeah, it's the whole thing like evidence generation and then verification takes like 15 milliseconds, and if you do it in 25 minutes, like hundreds.
So you're looking for passport-based exchanges rather than background checks, right?
Yeah, or partly passport.
Not necessarily,
Okay,
because for passport check, the server has to wait there with the passport already ready at the time when the client comes and connects. But in mobile settings, when we are actually like preparing the whole thing on demand, that's not actually good, because we are expressing the need for the resources, then we are still attesting them, preparing the passport, and then we are connecting. So there's no
advantage.
advantage at all.
So couldn't you prepare passports before the resources are
But
requested?
you would have to prepare it in the whole infrastructure, and you don't know where you will actually connect to. So that's the problem.
Mhm.
You would have to prepare it everywhere and for every user. Like that's
Because this offload workloads don't exist a priori. They are spawned on the exactly on demand, right? So
might be.
Yeah, I mean, there are different options here, but preferably we wouldn't like have pre-allocated resources.
because if you're looking at lambdas, for example, lambdas can stay warm. Right?
Yeah, yeah, I mean, there
Anyway,
are different options and different
Yes.
cases to make.
One more question about this. So, in the last slide, so what you are seeing here is that the PSK plus attestation in the handshake. So according to my understanding, at least, the attested TLS will not work with PSK based handshakes. I'm not sure if I missed something or.
Yeah, so we currently just do like use PSKs alongside the attestation. We took the draft as a starting point. I mean, was very suitable for this case. I think this TLS attestation draft. And then it does mention at some point PSKs, that there are some like the big picture showing it, but of course it doesn't explain any details of how to use it and how to, I don't know, use it securely, so that we actually have some binding between the key and the attestation evidence if possible, and these kind of things. So, but currently we are just using it alongside. I mean, we made our own prototype implementation and a bit like on. Well, not really specification, but just like put like PSKs alongside the attestation of these certificate messages. So, I mean, typically, of course, if you use PSKs, you don't have the certificate messages, but in this case, you would have what the certificate messages carry in the attestation. The evidence or results.
So what I was trying to say was that the certificate message will contain the evidence, right?
Yeah.
And in the PSK, you won't have the certificate message.
Normally you don't, but I think the TLS RFC, at least as I read it, it doesn't forbid you from using a certificate message, even if you're using a PSK. I'm not 100% sure of that, but that was.
Okay, so I think that's the use case when you have ECDHE plus PSK. Yeah. I would like to maybe later on, but try to understand the motivation of this, because in my understanding, at least it was that if you have already a feature key, so why would you need a certificate for that? But then we thought, at least in our understanding, and Arthur can correct me if I'm wrong, so we thought that this extension would make sense only for non-PSK based functions. So that was our understanding.
Maybe, we want to use ACMA. And ACMA is not ensuring that the underlying hardware is actually trusted. So we need to combine the ACMA shared key with the attestation. So that's why we need it.
And we can still, for the attestation part, we can still have some sort of an identity key, which we are like finding to the evidence. But then I guess it would be good if that would have some sort of a relation of binding to the pre-shared key, but we haven't really that way. We really just do them alongside each other. And these are some, I think it was actually the last slide one, 80% now, and these are open, basically questions. So questions also to the room, and this is so one of that was the second to last or bullet here was exactly this, that is this like a valid thing to do? And I mean, it's implementable, of course, and you can technically you can do it, but then is it secure enough? And we haven't done like any like really thorough analysis of that. It's just something that it's in our research. We want to be able to use PSKs and attestation at the same time, if possible, and using this standard way. And yeah, it's implementable and so forth, but it's what is the right way to do it? That has basically an open question. Sure. Yeah. One thing probably didn't mention it on the previous slide here, but so we wanted the PSK, using PSK was one thing, and then of course this we wanted to have mutual attestation after this partly use the passport model and experiment with it. Of course, the current TLS attestation draft, it doesn't have too many details about those. It mentions how to do it, and then you can extrapolate and create the message sequence for that too. I mean, there's the IoT and confidential computing cases, and it's just like if you combine both basically, then you get the mutual attestation as well. And I guess there's some in this repository where the draft leads, I guess there are some examples about the passport model, but then currently as far as I remember the draft itself. But so one question is that are they intended to be, or is it these things? Okay.
Yeah, I think we have issues already that's tracking this lack of details about.
Okay.
So definitely, passport needs more detail, mutual attestation. Yeah, we can do that. It just complicates the sequence diagram, but I think it's useful to have. But we are open to suggestions. Maybe so. If we are looking at a single gigantic SD that has the mutual scenario, or we want to have client to server, server to client separate, and then say, okay, now mix the features. I know we have different editorial options, and whatever you suggest is. We can do that, but definitely yes, the details about passports there to be ironed out, especially the need for identifying the verifier, right? So who are the verifiers that I support, and negotiate that thing up front, because otherwise how can you verify the passport itself, right? So there's maybe some previous literature about exchanging what are the CAs that you trust in pre-existing extensions in TLS that we could reuse, so maybe extending the extensions or mimicking what they do. Yeah, that certainly is a to-do item. I think the third question is the most important, and
Sure, yeah.
we need to discuss this. Yes.
And there's some, I mean, for us also, I mean, the performance aspects are important. So some maybe are more than going to implementation details, but then we also see since this draft basically it has this like I guess the key attestation step. So it's like has like 2 steps, but I don't know in this kind of a case where we want to not just example of key attestation, we want to like attest the full list or something, so it could be like reading in 1 step or something. So that is my question.
Right.
It could be maybe reduce the number of steps. Beneficial for performance in some cases. Yeah. The last one might be a bit out of scope for the protocol as such, but that is also of course and maybe not the most key question. It is also in context either that it might not be that long term, but of course there is this more general question at how do we ensure trust in like not just when we open a connection, but if we want to have longer, do we need to attest again, or can we get some like a random attestation information?
It's a pesky one, this one, because if you want to do that transparently in protocol, then you have to expose things, right? Freshness, lifetimes and stuff like that. So that can trigger then further exchange with post and shake stuff kind of thing. But I don't know. This seems like something that can be maybe explored at an application level. There may be some triggers coming from the stack, and then do the negotiation in parallel, and then swap connection, something like that. Like things that exist already in the mobile network for ASIC.
Yeah.
But I don't know. Yeah, to be discussed. It's an interesting point.
But yeah, I think that these questions, well, we have more questions, but these are the few selected ones for this here. And yeah, could be nice to discuss this more in the future, of course.
In the afternoon. Thanks very much. That was really great. Virginia, with phone.
Yeah, I think that may be nice. I joined the Zoom, so let me just share my screen.
Yes.
So I can switch on my video as well, so that's.
You not necessarily need to switch on your video, I mean, no problem, but the all is capturing your video as well. As
Oh,
we speak.
okay, all right. Well, I tell you what then, for the sake of the bandwidth, let me stop my video.
All of it's very intelligent.
Please look just. Okay, how is the audio coming through for people on the call? Do we need to move any microphones, or can people hear me?
Yeah, it's okay. I think it's a bit downsampled, but that's normal. Yeah.
I accidentally muted in the process.
Hello. Can you hear me, DM?
Yeah. Yeah. Perfect.
Not sure why the light suddenly flashes red when you move the microphones. That seems to maybe it's doing some recalibration.
I don't know. It seems very intelligent. So
It's just complaining about the new position it's been put into. Okay, Attested TLS use cases. Hello, everyone. Let me introduce myself. My slides have lost focus already. I'm Paul Howard. I'm a system solutions architect. I'm with ARM, and there are some details of my digital online presence there that you are welcome to make use of to connect with me if you wish. I've been with ARM for about 5 years. I'm up here in the team with Jonet. And also Thomas before we moved from ARM to Linaro. This is my first Linaro Connect. And what's my involvement with the Attested TLS project? Well, oddly enough, I am listed as a co-author on the draft. I think that's extraordinary. That's an extraordinary stroke of generosity by the principal authors of the draft. Because I've not actually been very involved with the design of the extensions. I did a bit of work on the POC, and that was principally around connecting the embed TLS server side with Verizon through the Rust client API wrapped in some C bindings. Which was an exciting piece of work for multiple reasons. To do the attestation verification on the embed TLS side. So I did get my hands dirty in the POC. But what I focus on these days is really, it's about how can we bring attested TLS sort of into the real world, I guess. What are some of the things we could do? What are some of the other use cases we could explore? TLS stacks we could extend beyond the ones we've already looked at, and how things might work end to end. And on that subject, I've got a couple of topics, and I think I'm going to cover them in reverse order from the agenda. So sorry about that, but the slides I have first are about attested TLS in service mesh. I don't know how we're doing time-wise on the agenda, but I might be able to rattle through both of my use cases reasonably quickly. So if we're running late, we might be able to make up some time here.
Yeah, we're late, but it's on my phone, so
So the first thing to point out is that I'm going to be covering,
Yeah.
just because the ordering of my slides, I'm actually going to do service mesh first, and then the other one after that.
we're already half an hour off, we're just.
Okay, all right, well, yes. Not sure I can go through that quickly, but let's see. Okay, attested TLS in service mesh. What's this all about? Well, so today I am wearing the Cloud Native Security Con t-shirt. I was at the Cloud Native Security Con in Seattle last year. And this year, when they are running the second instance of this conference, I wanted to put in a talk proposal to the CFP. And I was looking at things that are relevant to the cloud native community, but also wanted to bring in things like a confidential computing angle as well, talking about some of the stuff that we're doing in ARM. Of course, the difficulty with the ARM platforms is that they're not available in hardware yet supporting confidential computing, right? We're still waiting for that. So I had some challenges in order to pitch something that was relevant to the cloud native community that wouldn't be sort of blocked on the absence of ARM hardware. So I decided to think about attested TLS in this context, and possible use cases for attested TLS in the cloud native world. And the one that I hit upon was this idea of attested TLS in a service mesh. So why do people use service meshes in the cloud native world? So cloud native applications, they're built out of microservices. They're built out of small pieces that are talking to each other. And when you have a lot of distributed components talking to each other, there are a common set of challenges that apply sort of horizontally across all components that they need to care about. We do need secure and reliable communication between the services. So there needs to be TLS. There needs to be the ability for the services to discover each other, to do monitoring and logging and debugging, authentication, load balancing, network optimization, all of these things, rate limiting, policy management, all of the things listed there. And the idea of a service mesh is that they come along and they say, well, okay, we'll offload, we'll allow you to offload all of that furniture, so that the microservices can concentrate on doing the job that they actually want to do, which is being a microservice with a specific function. So service meshes basically take away the pain, I guess, of being a microservice in a cloud-native application. So this really is just a picture of what I just described. So service meshes quite often, the way they're architected is they use proxies, sidecar type proxies, so that the microservices are not necessarily talking directly to each other, but they're talking through a proxy, and the proxy then is the layer that is dealing with all of that horizontal management across all of the microservices, along with a management, a control plane that has to oversight of the whole thing. In the CNCF community, so there are two prominent CNCF projects whose names will come up whenever you talk about service mesh. One of them is Istio and the other is Envoy. Istio is a sort of wholesale management piece, the service mesh, whereas Envoy specifically is the networking proxy. It is the thing that you can deploy in a sidecar to offload all of those networking functions, including the TLS. So in an Envoy environment, all of your microservices are running, they are using an Envoy proxy, and the Envoy proxy is doing all the listening and transmission. Often deployed as a sidecar, so it might be like a separate processor or container. So why is this relevant to Attested TLS? Well, if you're using microservices and those microservices are communicating through proxies like Envoy, then the proxy is taking on all of the heavy lifting of secure communication, which means it is the proxy that is doing the TLS. So the question was, can Attested TLS help us enable use cases where we want to verify the security stance of the nodes that are hosting these microservices? So my pitch into the Cloud Native Security Conference was basically asking that question. You know, is this an interesting use case? I was going to use it as an opportunity to talk about this project and this collaboration and the Attested TLS work that we're doing, the POC work that we're doing, some of the CTA stuff and other things that are relevant. The talk sadly was not accepted. The conference was 4 times oversubscribed with submissions to the CFP this year, so competition was fierce. I didn't make the cuts, but that's okay because we have events like this where I can come and talk about some of the same stuff. So this is a hackathon, so I figured, well, shall we try to draw something that we could actually try to sketch out, actually try to build. And the idea that I had here was we could show a tested TLS between an Envoy proxy and any other peer, which indeed could be just another Envoy proxy, which would be typical in a service mesh environment. Now the Envoy proxy is written in C++. And it uses boring SSL as its TLS stack. Boring SSL, I believe, is a Google fork, I think, of OpenSSL, pinned down with some versioning and some functionality. And I know there is some work going on in this collective group. I don't know, is it represented by anybody who's actually here today?
Aston, unless he's joined the. No, it's not here.
Okay, well, anyway, in the wider collaboration that we're doing here, there is some work going on to look at implementing the Attested TLS extensions in OpenSSL. I believe it is possible to build Envoy in such a way that it uses OpenSSL directly rather than boring SSL. I think there's a community effort that has validated that as a possible thing to do. So I believe that is achievable. I think also it is possible in Envoy to hook up the certificate validation to basically bring in a custom validator. The reason why I think that is possible is because I think it was already done with Spiffy. I think there is a validator for Envoy that will use a Spiffy Aspire validation service. And I was thinking, well, an interesting nugget to build would be a certificate validator that takes an evidence bundle, an attestation credential, and sends it to Verizon through the C clients, the same C clients that we created. The Envoy is C++, but of course C++ to C is a fairly straightforward story. So this was an attempt to sketch out a small piece of working stuff that it might actually be possible to build. But I think also in the context of today, I wanted to consider this not just as a single thing, as a single bounded hacking exercise, but also, what are some of the wider questions around this? So I wanted to put some of these open-ended questions and discussion points into consciousness for the collective here to be thinking about, such as, whether passport makes more sense than background check in a situation like this, whether both make sense, whether, there could be use cases for either. The other question I think around this that's kind of interesting is how we blend this with some of the work. So some of the workload attestation and node attestation ceremonies that already take place if we're using SPIFFE and Spire. Let me just flip on to, I've got to have this appendix slide. SPIFFE and Spire, for those who don't know, so SPIFFE is short for the Secure Production Identity Framework for Everyone, I think. And it is basically a means. SPIFFE is a specification, and it is a way of assigning identities to workloads. And Spire is a production grade implementation of the SPIFFE spec, essentially. Now, the way SPIFFE and Spire work is that a workload, such as a microservice, will be executing on a compute node of some kind. And what a workload needs to do is to be able to prove that it is worthy of an identity. And a Spire server will award it that identity based on a whole sequence of verifiable credentials, attestations, in other words. So in Spire, you can attest both the workload as shown here over on the left, but you can also attest the node, and it's very, very pluggable. So you can do arbitrary types of attestation, and you can get all sorts of different types of evidence, which can then be verified on the server. And based on that, the Spire server can then choose, well, is this workload worthy of the identity that it is claiming? And if so, it gets awarded a JOT, I think it is basically a JOT document that is that SPIFFE identity, along with the relevant signatures to prove its worthiness. Now, the reason why, going back to my open discussion slide, the reason why that's interesting in combination with attested TLS is that these two things might sort of compete with each other, or they might overlap, well, let me rewind and sort of phrase this another way. When I was thinking about my pitch to CNCF, I was thinking quite naively about this idea that if you had a service mesh and you had a whole load of workloads running on disparate nodes, and you wanted to kind of throw a global policy switch across the whole system that says every node in this service mesh has to be running in, say, a confidential virtual machine, or a trusted execution environment, regardless of what their identities might otherwise be. I just want to make that decision globally across the whole system, and then use attested TLS with the attestation credential to prove just that one aspect of the whole mesh. But I think, possibly that's a naive view, because I think if you take the SPIFFE and Spire view of the world, I think probably this policy of the compute node has to be based on, has to be running within a trusted execution environment. That would actually be one of the criteria on which you would award the identity, right? So the identity would just not be awarded unless it has that provable characteristic. So I think this idea of like a policy switch that you do in the service mesh, whether that would work in practice in a cloud native world where SPIFFE and Spire are also actively used, I don't know, right? They might sort of, they might compete with each other somewhat awkwardly. So I think that's a question we just have to explore. I don't have all of the answers, and I never planned to go into the conference with all of the answers either, right? It was partly supposed to be like a discussion, seeding it into consciousness of the expert community and to see what they think. There is also Whimsy as well. So Whimsy is an effort that's going on within the IETF. Again, looking at workload identity in these sort of disparate distributed environments, doing some things I think similar to what Spiffy and Spire do conceptually. And I know they are collaborating. That's another effort. There's a working group inside IETF that is looking at this as well. So the applicability of Attested TLS there, I think, is also something we need to be thinking about. But yeah, these are the open-ended questions. I still think, in terms of just a hackathon piece, a bit of code that's interesting, might be doing something like this, just to see whether we could do it. Can we hook up the pieces?
But the proof of concept here would be understanding whether there's any boring SSL specific extension that is used actively by Envoy that
Yes.
is not available in stock.
Yes, indeed.
That's
So there's some discovery here to see whether,
that would be.
if you strip out boring SSL, replace it with open SSL,
What is this?
can you still do custom certificate validating, for example? Because if you can't, then we've got a bit of a break in the stack there. That's fine though, because I still think even if we couldn't use open SSL, the idea of creating a certificate validator that talks to Berets on with an attestation credential is itself a useful. It's a useful nugget, but it is only a nugget, right? It has to be considered within the scope of some of these more open-ended questions about how would this actually intersect with other identity mechanisms that are using attestation-based credentials.
Can I talk?
Please.
Number two, the blending, I think we're in good place because if we allow certificate-based and alongside that there's evidence and things in the same
Yes,
flight, then
Yes.
you're good to go, right?
yes, I agree, right? So, and I think this is why, I talked before about this idea of a policy switch. If you were using Spiffy and Spire as your identity mechanism, and therefore it's all X509 SBIDs, the Spiffy identity documents that are in the handshake, then if you have this additional piece of policy, you could put it as an attestation credential, which is independent of the identity. So I think it does work. But whether anybody would actually deploy in that way, I don't know, right? And that's a question for the cloud native community. That's why I wanted to go to the conference. That's why I wanted to have that conversation with the audience there.
I think that's a conversation.
Yes, it's still
From
very
my
much.
perspective, that's. And then a question on your third question, which is applicability to music. You mean the ability to survive cross-domain authentication? So, for example, the verifier in one cloud is Verizon, and in the other cloud could be another thing, or there could be no attestation based identity in that cloud. So you need to sort of so distribute, for example, so to create trust relationships between identity providers and both things.
Yes, I mean, I guess, all of that.
Okay.
And probably a lot more besides.
Yeah, there's a lot of back.
Yes, Spiffy and Spire has the notion of a trust domain and everything works within. It is sort of bounded, and I think maybe that part of the idea of Whimsy, I guess, is that it's zooming out from that, right? It's going, okay, you might have 20 Spire trust domains. Have you linked all of those?
Coordinate, yes.
Yes.
How do you harmonize the credential formats across the various things so that everyone can understand?
Yeah, so I think, at some point it might make sense to have a sort of virtual roundtable with some Spiffy people and some Whimsy people and, some of us and talk through some of this.
That sounds like an excellent idea for a side meeting at next day. Yes, for example.
Yeah.
I know one of the developers of Spiffy Spire. So he used to be
PhD student of my professor, so.
Oh, right, okay, who is that, just out of interest, I might know.
Andre Brito.
Sorry,
Andre Brito.
Andre Brit, okay.
Exactly.
Oh, okay, I don't know, I don't think I know them. I do know, I know Andras Vega, who is another spiffy aspire luminary. But I can't remember where he is now. He was a control zone for a while, but I think he's still there. But yeah. Okay,
Awesome.
so that was one of my two topics. Any more questions on this one? I can roll on to the next one. Stop in silence.
Yeah, I mean, the first question was already in,
Yeah.
Andre and
Yes.
engine is, so. Nice to go.
Okay, no, that's my fault, that's fine. Okay, so this is speculative use case number 2. What I call logical T across cloud and edge. We've seen this slide already. Thomas and I both stole the same slide. I think from Jonat's excellent FOSDEM presentation a year or two ago. So these were, not sure whether flagship is necessarily the right word, but these were our leading 2 use cases for attested TLS in the early conceptual stage. One where you have your onboarding some sort of edge device to a cloud service and using it as a station above and beyond just the proof of possession of the private identity key. And the other is this handshaking with a peer that's running inside a confidential computing environment, and you want to verify the confidentiality before releasing secrets and sensitive stuff and all of that. So I did my usual thing and thought, what if you did a little bit of both? It is kind of a little bit of both, right? So this is the overall idea, and we are at the Narrow Connector, and I've been thinking about confidential computing on the cloud and also ARM platforms, and one of the things we find more in the ARM ecosystem is more edge devices, more devices that are running outside of the cloud, doing things like gateways, for example. We're often finding the ARM architecture employed in that kind of space, and of course ARM is bringing confidential virtual machines as well. So the idea was that this concept of a sort of logical trusted execution environment, which is spanning across the cloud and the edge. So if I'm a workload owner, if I am the tenant of a cloud, but I don't trust the cloud provider, I am willing to trust a workload that's running inside the cloud, provided that it can prove itself to be confidential and isolated from the hosting infrastructure. As a workload owner, I may also be the owner and administrator of some single tenant devices that are running outside of the cloud that I am also willing to trust. But again, not blindly, based on some verification of their security stance as well. And then the way those things will talk to each other might be through attested TLS. And it's really just about it's really just about understanding what kind of schemes you might use mutually to achieve something like that, right? And I think this one is sort of feels to me like we could probably already do it, because I think we already have mutual attestation supported in the draft, right? The design copes with that, and the design also copes with different data types and different credential types flowing in both directions, right? There would be no need to use the same type of attestation credential client to server as you do the other one. You could have those things be different. So for our platforms, there are two relevant attestation schemes. There is the CCA attestation, and there is also, as part of PSA certified, there is a PSA attestation scheme as well. And PSA certified is increasingly used as a common security architecture in like microcontrollers and some of the smaller devices, and it includes functional APIs for things like crypto services, but also for attestation as well. You can get a platform attestation out of the system using APIs in PSA certified. So here's the what could we build piece. Now the idea here is that some of this is based on bits we've already done, right? So in the POC, we already have the capability to do an attested TLS handshake between embed TLS instances. So I think if you had a Verizon service as your verifier and you endorsed it with a PSA platform, golden description, and the CCA platform, golden description, and you had a handshake between an embed TLS running in normal world on an edge or endpoint device, and talking to a PSA attestation service in the secure world. That is something I think we could possibly achieve using the same sort of parsec style stacking that we've done in the POC, right? Because we have
Parsec is missing in.
Yeah, I didn't put parsec. I ran out of both space and time.
Because you need the key attestation thing that is.
Yeah, exactly. Yes, I should have put parsec on there because well, I feel a traitor to my own kind because I was heavily involved with the parsec project in ARM a while ago. Yeah, so using parsec as the abstraction over the attestation interfaces on the platform. We have already hooked up parsec to PSA services in secure world. We've not done it for attestation, but we have done it for crypto. So I think it's small matter of programming. I'm looking at Yonat to get not of the head cues from Yonat are encouraging at this point. I think we can do that. I think we can do, and also on the CCA side, this is something we have already started looking at. So I think this would be an extension of the POC. Maybe we could run it on like virtual platforms, for instance. There is we could use an ARM reference platform like Corestone or something. I don't know, maybe on to represent the edge device, and then of course we have the virtual platform running the CCA stack, which we already have the capability to do on the CCA side. So I think quite a lot of this would be glue and bolting together and build scripts, and we could show this bi-directional. So yeah,
I think this is a low-hanging fruit for the bot that we're in.
Yes. I think so. I think it would just be like another personality or another incarnation of the bot.
And it's a good idea to frame it as this, the logical teaser of the very long bus, as you go past the next step.
Right. Yes. Yes.
And compare and contrast with how that look like from, say, for example, from an SPDM perspective instead, right? Like if you look at it like a device assignment exercise done differently using TLS rather than SPDM. That's an interesting one. Cool.
Okay, I think I had some open-ended discussion points on this one as well. Yeah, I mean, I think the thing about this is sort of you're slightly trespassing into areas where the cloud providers have proprietary solutions, right? The cloud providers like Azure and AWS, and I don't think Google Cloud does, but this notion of bringing edge devices into your cloud and having management and orchestration of, say, containerized workloads, pushing them out, having lambdas executing on the edge, for example. You know, TLS is already built into the cloud providers, and they have edge management platforms for this. So if you were to do something like this kind of bi-directional attestation, you would need to. I think you'd sort of need to do that in collaboration with the cloud providers to some extent, right? They would have to understand that this is something we want to do. They would need to be collaborating in it, because otherwise, how do you hook into what they're already doing with their, you know, they're doing deep TLS magic already.
This was Susanna's slide, right, where we had a deployment block that collaborates with the implementation.
Mhm.
It's back into there, yeah.
Yeah.
We haven't identified who those guys are, but you're right, that's, there's a, for example, the green
Yes.
glass people or,
Mm.
yeah, or other cloud, maybe Azure is similar thing. I don't know.
Yeah, and this also who and where are the verifiers if you're doing, you know, doing two very different styles of attestation credential in each direction. Are you talking to the same verifier? Are you talking to different verifiers? How do you discover your verifiers? And now, you know, how is that whole system bootstrapped such that going back to the start, the workload owner knows that they do in fact have a logical T. They know that they have trusted verifiers that are going to that are going to validate the logical T, and that's going to be something that.
Yeah. You're right, that, you know, naively, looks like from the trust relation perspective, the workload owner role could overlap with the verifier owner role in the REST architecture. This guy is the guy that sets the policy and owns the verification feeds. We necessarily need to be shared here, but that may be realized differently in the sense that could be the verifier owner of two different verifiers.
Yes, yeah, it's where it gets interesting, right? I think also there's another entity on here that I've not represented, but you know, I couldn't get through this whole session without mentioning AI at some point. You know, otherwise, what's the point? So obviously, AI at the edge is super important, and I think a workload owner is probably not the only entity in here that matters, right? I think there may be an application provider, and there may be a model provider as well. Like they may be the owner of a trained AI model that they are not willing to just expose publicly unless it's going into an environment where they know it's going to be protected. So if you want to do AI at the edge, that means your model may be moving to the edge. You know, how do you create the suitable guarantees that actually all of the entities are going to buy into and agree that yes, this is indeed acting as a logical T. I can trust that my trained weights are not going to be stolen, because there is valuable IP in AI models, trained AI models.
That's very true, but from, you know, looking slicing the problem from just a Attested TLS perspective, this is your fault, right? It's
Absolutely, yes. Yes, but I think it's important to consider the entities when talking about the verifiers.
Yeah, the verifiers could be somewhere. They could be also, again, like part of like the logical TEs, just the workload provider, or like all the entities involved that rely on the result that we are in a logical TE need to have some bootstrapping mechanisms to the verifiers. So in the end, it could be very different verifiers when we're talking about also cloud providers. They could be from the cloud provider, as long as the person that is interested in the properties that we have the TE can have a way to verify that the verifier is actually verified.
trust them, right?
Yeah, exactly. But yeah, then you can not remove the problem, but you can probably delay the problem.
That sounds good, yeah.
Yeah, so you put a in a different abstraction layers,
Yeah,
pretty much.
No,
So
I-
then you can say,
yeah.
okay, the technical verification happens, and then how the bootstrapping and the organization stuff of like the actual deployment workload
Mhm.
is then a problem that is then outside of the actually local attestation, or not the local one, the attestation that is happening in the environment itself.
Sure. Yeah, makes sense. That's me, that's me done. That's my two use case segments. Thanks for the discussion and for your time for listening.
Thank you very much. We're very nice contributions. Ah, break. Finally. But we are super late. Do you feel like you want to rest your brains, or should we continue? I don't know. Because the risk is that we then delay lunch. That's more. I don't know if brains, bit stomachs, or
Could we maybe have a short break, just
Okay.
as like a comfort of a coffee?
so like 10 minutes rather than.
Sounds good.
And after that, Ian, it's you, right?
Yeah, that's me.
You see.
Yeah. Are we waiting for more people?
Oh, yes.
Andre is missing. Maybe we wait for him.
Yeah, I think it would, that very,
We can, do you think we can start or?
I think it.
Okay,
Yeah.
yeah, you go.
Great. Okay. So yeah, for those of you who don't know me, I'm Guillaume Bryant. I've been working for ARM, based in Cambridge for the past 4 or 5 years, mostly focused on confidential compute. More recently, I've been working on Veracruz, which is a project adopted by the CCC. And today I'd like to talk about the intersection of DPUs and confidential computing. So DPUs are just, an acronym for data processing units. You probably heard about smart NICs before. Well, it's essentially the same idea. So yeah, first I talk about that, where we're coming from, the problem we're trying to solve. I'll try not to dig into details too much because I think a lot of things are going to be orthogonal to the discussion today. And after that, I'll talk about Attested TLS and how it could fit, and how it actually fits in the work that we've been doing. So this is going to be an informal talk, so feel free to jump in anytime to ask questions. Just to confirm that everybody can see my screen, yeah?
Yes, yeah.
Yeah. Great. Okay. Right. So confidential computing has been, there's been lots of efforts around making confidential compute more practical, more usable. For example, we moved from in-process enclaves like SGX, Trust Zone, to blind hypervisors like TDX, AMD, CBS, and P. That's great. There's one limit that could actually be problematic in some scenarios. This limit is that confidential workloads nowadays are still mostly restricted to CPU-centric tasks, so general purpose computations, and that could be a problem in some scenarios. Let's just take, for example, ML training. Imagine you're an ML company, you want to build a model. You don't have access to the systems to train your model. So you want to outsource it to the cloud. And the first issue is that you're going to have to trust an entire ML data center. So it's going to be a complex system encompassing not just CPUs, but AI accelerators, network interfaces, storage devices, and so on. And all those devices are going to process your data. So your data is going to transit between all those computing nodes and processed on those nodes. So yeah, that's an issue that nowadays confidential computing could not tackle, even though there's been some effort from NVIDIA, for example, towards making GPUs more, multi-tenant oriented. They came up with some kind of attestation protocol, but as far as I understand, it's not widely available and used yet. So the other complications will be, what we just talked about, multi-tenancy, and the fact that the cloud provider and tenants don't necessarily trust each other. So we propose to make confidential compute even more useful by trying to allow CPU enclaves to connect with other devices and to establish trust with them. So as a first step towards that, we decided to focus on DPUs, data processing units, because they're quite multi-tenant oriented. They're already used by hyperscalers to outsource, to offload some infrastructure functions. We'll talk about this in the next slide. So it's a DPU. So DPUs are part of the trend of accelerating computation and coming up with devices that are, well, specialized but still programmable, highly programmable. So GPUs are an example. DPUs are another example. So they specialize in infrastructure functions. And what I mean by that is things that are not guest workloads. So imagine take AWS, for example. You've got a bunch of VMs, right? And customer code is running in those VMs, right? But the thing is, there's a lot of overhead that is not part of the guest workloads. So you're gonna have to process communications between VMs. You're gonna have to process communication from VMs to the outside, the data center. All that has a cost, and that's when DPUs come into play and accelerate those kind of IO-driven tasks for the traditional hosts CPUs. So we can see that DPUs are great at high performance networking. They can accelerate TCP. They have some TCP offload functions. So aggregation, TCP aggregation, segmentation, calculating checksums. So essentially what a smart NIC is doing already. They have some acceleration for packet processing. They have some interesting security features, security functions. They can accelerate asymmetric crypto, symmetric crypto, hashes. They can be used for RNG. They have a true RNG on their SoC. Can be used as a hardware root of trust. In terms of storage, they can accelerate decompression, and they can expose NVMe devices to VMs over the network. So yeah, that's pretty interesting for hyperscalers and cloud providers. There's already a bunch of them massively using DPUs. To give you some figures of why it's interesting for them, there's been a study from NVIDIA's partners. I believe Ericsson was part of them, and they showed that using DPUs could reduce energy usage by around 20% to 25% compared to traditional CPU-centric servers. So that's in terms of energy savings. Now, in terms of performance, they showed that you could get up to 50x more throughput if you're using DPUs as opposed to traditional servers.
Can I interrupt you a second? Maybe
Yeah, of course.
GT, but since you talk about IPsec offload, is there a sort of attested IPsec or attested IPv2 lurking as a possible extension? So we could say, for example, port the ATLS mechanics to IPsec to the negotiation as well, or so. I mean, how are these IPsec tunnels? So is IPsec prevalent in the context that you're using, or And you're trying to replace that with TLS, or is it something
Right.
that it's just orthogonal to that?
Right. So at some point we consider using IPsec for what we wanted to do. I'll talk about this a bit later. But no, it's not really relevant here. IPsec is not really relevant, right?
So sorry.
Yeah, maybe I shouldn't specify IPsec here, but yes, I'll talk about the use cases we have. But basically, yeah, some of the use cases are entirely about offloading TLS to DPUs and attestation to DPUs. Yeah. Any other question on this? No. Okay. So I'll quickly go through what DPUs can look like from a systems perspective. So, just like we talked about, there's a trade-off between performance programmability. And for that reason, there's a lot of different DPUs. Like there are some CPU-based DPUs. Other DPUs, even using CPUs, are also using FPGAs, for more specialized tasks, while still retaining some form of flexibility to reprogram the FPGAs. Others DPUs are using ASICs. And all that comes from, a lot of various software stacks. There's a lot of fragmentation in this ecosystem. There are some efforts from the Linux Foundation, OPI, to try to reduce this. So from a purely system perspective, DPUs typically are a system on chip. So it's a PCIe card that you plug into a host, typically. The host being the server in a data center. So it's gonna comprise a bunch of components. Typically, it's gonna have a CPU subsystem for general purpose computation and to manage the system. There's going to be, of course, some high performance network interfaces. Usually, they support either Ethernet or InfiniBand. You can configure them. The latest DPU models, they support about 400 gigabit per second, to give you an idea. There are some hardware accelerators for crypto packet processing, what we talked about on the previous slide. And finally, there's a PCIe fabric to allow all those components to communicate and to communicate to connect the GPU with a bigger system. So host CPUs, they can even connect to GPUs and storage devices and so on. So here we have an AMD Pensando on the left side and an NVIDIA Bluefield on the right side. There's a lot of the brands. These are just two examples. Okay, so now let's talk about use cases at the intersection between confidential computing and DPUs. So we came up with two use cases. This is not an exhaustive list. These are just two interesting use cases that we deemed interesting, at least. So the first one is vicarious attestation. And the idea is that if node A already trusts node B and node B already trusts node C, then there's a reason why node A wouldn't trust node C. So the idea here is that we could use DPUs to completely take care of everything related to attestation. So there would be a node hiding behind the DPU, and the DPU would take care of attesting all the nodes on the network, and thereby creating some kind of trusted network where any host connected to this network through the DPU would already trust all the endpoints of the same network. So we could get some kind of VPN or virtual private cloud where we could establish a secure and attested connection with pretty much any node on the cloud, but also outside of the cloud, on premise, for example. So that's what we can see on the right side. We've got a host in the DPU. The first thing that happens is that the host at the bottom attests the DPU, and then can provision it. So you can offload some workloads into an enclave. I forgot to mention, but everything green here is a TE or an enclave. And once the DPU is attested, then the host can ask its DPU to attest other nodes on its behalf. So here, the first DPU is attesting the second DPU on the top on behalf of the first host, so on the bottom. So that's our first use case. The other use case is confidential offload. So it's something I just talked about. Is the idea that you can attest and provision the DPU, and the DPU will take care of a task that it's good at on behalf of the host CPU. So for example, what we were talking about is TLS offload. So we could offload not just the handshake, but also record protection to the DPU. We could even go further and offload some TCP logic to the DPU. And in addition to that, well, the DPU would have access to the plaintext inside its enclave, so it would be able to enforce any kind of policy on traffic. So it could behave as a confidential middle box. So it could be used for threat detection, IDS, mitigating data leaks, enforcing privacy regulations, this kind of stuff. Any question on this? No. Okay. Okay, so just quickly, I'm going to go over the threat model here. Oh, okay. So on the left side, we've got the DPU. On the right side, we've got the host. So we're assuming here that those two devices have a TE, which is not necessarily granted. DPUs nowadays are not shipped with CPUs capable of supporting enclaves, hardware enclaves. So this is a bit speculative, but we can imagine that in the future we can have something like that. So we would have those two devices, and we would have confidential VMs on the host side, establishing trust with the DPU on the left side, and we would use something called TDISP, which is a protocol that the PCI SIG is currently working on. It's still a work in progress, but the idea is that you could use this protocol on top of PCIe to establish a secure channel that really looks like TLS between a confidential VM, so basically a hardware-based enclave on the CPU side, on the host side, and then a virtual function on the PCIe device side. So yeah, at the moment, there's not really any device that supports this protocol yet. So yeah, this is speculations for now. The other thing is that this threat model here could vary widely across DPUs, because every DPU, comes with its own architecture. But the idea is that if you want to offload, say, TLS from the host into the DPU, then you wouldn't have to trust the NICs, because all the traffic going through the NICs would be encrypted. The only thing you would have to attest would be, only is, a euphemism, but yeah, essentially you would have to trust to attest the enclave on the CPU subsystem, the DPU side, and then you would have to trust all the accelerators and security engines that the DPU is using in order to process, to execute the workload that you're giving it. Okay, so now I'm going to talk about the actual work that we've been doing and where Attested TLS is going to fit in. So we develop a framework to explore the two use cases that we just mentioned. It's available on GitHub. It's mostly written in Rust. And by mostly, what I mean is that, well, it's using the attested TLS prototype. So there's quite a lot of code that's, written in C because it's based on embed TLS. So we're using attested TLS to establish trust between the nodes that we mentioned here, and to be able to control and provision them later on. So first, why do we even need attested TLS? So I think we can all agree that attestation and TLS is better than TLS, assuming that T's are a success. We would just get better security guarantees by using attestation and TLS. The other thing, if we're comparing attested TLS to attestation plus TLS, is that it's better in that we're combining those two things into one single protocol and one standardized protocol. So it makes it less error prone. Imagine if we were using attestation and TLS separately. Even if the stacks we would use would be sound, it would be entirely possible that the integration between the two stacks would lead to epic failures, like having TLS but not having attestation. So yeah, using both of these at the same time kind of guarantees if the implementation is correct that we can have both attestation and confidentiality at the same time. The other reasons are, well, pretty much what Thomas mentioned earlier, that we might require less back and forth between the two TLS endpoints by using, attested TLS. What I'm not entirely clear on is if it would be actually more scalable than certificate-based solutions. So in the past, in Veracruz, we were using something other than attested TLS. We're basically encapsulating evidences as part of the certificates. So yeah, we're still in the process of benchmarking this. It would be really interesting to see how those two solutions compare, and how attested TLS compares to traditional TLS. It'd be very interesting to see what kind of overheads we're getting from all the back and forth between relaying party and attestation service, or attester and attestation service. I've got a slide about this soon. I'm just going to talk about the software architecture quickly. So the main dependency of our project is attested TLS. So we're using it. I'll talk about the network protocol on the next slide. We're using it as part of our transport protocol. I'll talk about this in the next slide. So yeah, something interesting to note here is that I've used the attested TLS POC, but I'm using a Rust wrapper around embed TLS around the POC. So we're simply reusing the two branches that are made available on Unit's and Paul's GitHub, but the TLS client and server have been rewritten in Rust. So that's the big difference between what we have in the attested TLS POC. Yes, I'll show it here. So this is an overview of our network stack. So we have host and DPU on one side, node on the other side. So TLS is only used between the DPU and the external node. It's not used between the host and the DPU because we're already assuming that we will have, this TDISP protocol that I talked about, and that we won't need a TLS connection between the host and the DPU because it will already be implemented in hardware at the PCIe level. host and DPU. So yes, we're using Attested TLS between DPU and node at the moment. There's just one caveat, but I'm actually not clear on that. Earlier, Thomas mentioned that that mutual Attested TLS was supported, and I really thought that it wasn't. So for all this time, we've been using the Attested TLS stack in a weird way. Basically, initially, it was meant for an IoT use case where the IoT device was the relaying party, and the edge device or the cloud device was the attester. So the prototype was, at least I thought that the prototype was assuming that the attester was the initiator / client. But in our case, it's actually the opposite. In our case, the host is the initiator and the DPU is the responder. And so the way we're using it, we basically, the TLS server is basically running in the host, and it's initiating the connection to the responder, which is on the DPU. So we're just piggybacking TLS on a TCP connection that the server is initiating. So it's kind of weird, but yeah, just wanted to talk about that. We have some early results, but you should take it with a pinch of salt, because they sound a bit weird. The experiment we've been running is, so we have two different machines. We have the attester and the attestation service running on the DPU. So that's, a bunch of ARM Cortex cores. And the relaying party is running on a separate machine, on ARM N1s. And we're measuring the handshake latency between those two machines. So yeah, just to mention, we're running the attestation service on the same machine as the attester, because we're assuming that maybe it would make sense at some point to cache attestation results, like to have some kind of cache hierarchy of the attestation results. That we don't want to go back and forth between the attester and the attestation service like all the time. So yeah, these are the results we have. There isn't much to say about this. The handshake takes almost half a second, which is a very long time, especially with machines on the same network. We still have to investigate this. We just got the numbers yesterday, actually. So we still have to investigate this. There's a good chance that some binaries were not compiled in release mode or something like that. Because, yeah, 400 milliseconds sounds like an awfully long time. So this measure of handshake latency was absolute. We didn't have a baseline. It's something that we could discuss. What kind of baseline could we have to benchmark Attested TLS? We could compare it to traditional TLS and see what's the overhead of first of all getting the measurements from the VTPM, and then communicating with the attestation service. That could be interesting. The other thing we could do would be to compare Attested TLS with traditional TLS with the thing I was talking about earlier, so attestation evidence added to the certificate, which might be basically what Attested TLS is in some cases, but yeah. So yeah, in terms of future work, so we love to finish this benchmarking, and we're looking forward to exploring other use cases around DPUs. So we really want to explore what software orchestration would look like if the DPUs are orchestrating. So something a bit similar to what AWS Nitro is doing. We love to see how attestation behaves at scale. So when there's a lot of nodes attesting each other in the data center, for example. And another use case would be confidential middle boxes. So yeah, pretty much the use case we talked about earlier. And that's it. Is there any questions?
Yeah, a few, but maybe some notes. No,
Yeah.
so I can go ahead, right, again. So I have a few observations and some questions that we jotted down. The first one was the DPU to host attestation flow seems to be inverted compared to the normal this conversation, right? Where
Yes.
is the host that asks the device, get attestation from there so that they can verify that you're good enough for my case. So my question is, does that need this inversion needs an extension into this, or are you making the traditional flow and then when you provision the node with the station, when you're setting up the TLS context, then you basically the host gives back the whole evidence package comprising the DPU pieces. Because as far as I understand, the DPU node will then, when negotiating with the other, the TLS peer needs to send the whole thing, right? So host plus device attestation is not just the device attestation or the host attestation, is the composite attester log that needs to be sent over. Or maybe I misunderstood
So right.
the
So
problem.
so are you talking about TDISP in particular, or are you just talking about
Well, I'm talking about because so what kind of evidence do you exchange in the attested TLS handshake? Is it just the DPUs coming from the root of trust of the DPUs, or is combining the RTR from the DPU and CQ in one package? That's my question. And whether that has an implication on how TDISP communication works and basically SPDM.
right. So the idea, so it's not implemented yet, but the idea is that TDISP would only be used between host and DPU.
Yeah.
So it's so the thing is, yeah, that's kind of the crux, I think. TEE will have a different meaning for every device manufacturer, I think. Yeah, I don't think there's any standard yet for what the TEE would look like on the PCIe device. So yeah, so the measurements will vary. I don't think every device will have the same kind of will provide the same kind of measurements to the confidential VM running on the host. So yeah, so I guess that answers the to this side of the question. Right. Yeah.
Well, maybe we can take this offline, but it was more on the composition of the DPU root of trust and the host root of trust. When you present yourself to the TLS peer, what kind of trust matrix are you presenting? The DPU only, the DPU plus the host, or the host alone? I think you need both, right? Host and DPUs measurements and evidence packages, right? To be combined together when you negotiate with family, right? And in that sense, my question was, I was not clear about how, because nowadays the get attestation on SPDM works the other way around. So it's the host that requests that to the device. Whereas here it would be the device that asks, give me the package and then we use that, to negotiate my TLS channel. So yeah, it was basically whether SPDM allows flipping the direction of the request.
Okay.
Whether.
Okay, I get your question now. Yeah, so as far as I understand, SPDM and TDISP are assuming that the host is the initiator slash master. Yeah, I don't think they're considering, for now at least, a mutual kind of relationship between the two entities. Yeah. So yeah, that's a good question. Actually, it's something we were thinking about, because now for now we've been assuming that the host would initiate everything, that the DPU would be the responder, would only be the one, always serving the host. But we actually have some use cases we'd like to explore where the DPU is the one controlling the host. It's kind of what AWS Nitro is doing right now. They have the control plane is running on the DPU, and the DPU is controlling is spawning VMs on the host CPUs. Yeah, so I don't know how TDISP is gonna play out in this case. Yeah.
So that answered my question. Thanks very much.
Oh, great. Yeah, no problem.
And then I had another one, which was not necessarily a question, but it was your sort of compare and contrast the attested TLS solution to an attested CSR solution. Like you have invariants already where you sort of enroll into a CA via an extended CSR that includes evidence, right? So you get that back a normal X519 certificate, and then you can use that to negotiate. And I think that's a very, very valid comparison. So I mean, I'm very interested in seeing in terms of overhead what that means. So benchmarking that will be very interesting, and also I suppose there's going to be some freshness versus performance trade-off there, because then we need to really size the certificate lifetime so that it is in sync with the freshness policies that you require on both ends, right? But this is very similar to using a generic passport mode. So I don't think that's very different from using pure attested TLS with passports. Except maybe in attested TLS with passports, passports are small things like JOTs or better. That might be, performance-wise, it could be slightly better thing. And in terms of benchmarking, I think Carsten, who's not here now, but is very close. He has done some work already, and I think if you connect with him and you can share some of your insights with him and vice versa, that would be a great thing. So
I think he's online.
is he? Carsten.
Yeah, hello, can you hear me?
Yep.
Yes. Yep.
Okay, yeah, so I'm online. I can see the slides, so I don't know how comparable they are, but yeah, we can certainly take a look, see what we have on our testbed and how these numbers come to be.
Yeah, that'd be great.
Designing a benchmarking methodology, saying what the baseline is, and going from there, maybe 12 homogeneous or comparable results. Then, so that great thing. Just a suggestion. Okay, but yeah, again, this write certificate client with 200 and plus milliseconds look very dodgy.
Yeah, that's a lot of time. Yeah, I haven't really had time to process the results. Someone got the results for me, and yeah, I'm very suspicious about this. There's 300 milliseconds.
Sorry, there's no critical. It's just pure audio, so that sounds really strange.
Yeah, it does. Plus, the two machines are in the same network essentially. Yeah, I mean, even if they were millions of kilometers away, I don't even think we would get 200 milliseconds. Anyway, yeah, we'll have to look into that. Yeah. And yeah, I didn't mention, but this includes both CPU time and IO. So yeah, it might be more interesting to isolate those two things.
Awesome. Any other question? So thank you again. That was an awesome contribution. Thanks very much.
All right. Thanks for your time.
Looking forward to collaborating.
Yeah, sounds good. I'm gonna stop sharing.
Gene, you're still on?
Yep. Then speak also about this. So yeah, this is very clear direct continuation then of the previous presentation we had. So we have this a prototype implementation of this whole offloading framework that's written in Rust. So for this implementation of TLS attestation, then we also chose a Rust native library, so the Rust TLS that we're using. So the base in this case. And yeah, so we can hear the thing that we mentioned earlier. So we have the Rust TLS, but it didn't have support for TLS PSK from before, so we added that. And well, the detail here is that there is also sort of an extension to the TLS tree specification, which specifies how to use these like external imported pre-shared keys in a certain way. And we implemented this solution so that it actually requires it.
I don't remember, sorry to interrupt you abruptly, but is 9258 a standard or is it experimental? What's the status of it?
Should be, I think, or is standard.
It was proposed standard. Okay, well, thank you.
And in this implementation, we focused only on basically the protocol part. So there's this like a real evidence generation and verification. These things we have not integrated with it. So we, I mean, we can generate attestation reports and do verification, like of course. Otherwise, we have some numbers like standalone numbers from that part. And then we have some measurement results from with this actual prototype, and then we have like added it together so that we have like some synthetic results that we can come back to that and break it. Yeah, so this is I don't know if we these details are not so well visible here and notice, but we just yeah, this illustrates like the server attestation case where we had these like this case alongside of the evidence here. So yeah, background check model based attestation. In this case, handshake. That was one part that was implemented, and then it was also I need to give a bit more details because this is then the mutual attestation exchange. So some of the details here might be actually a bit weird. For example, there are some signatures are very so this was like an early version of the exchange. I think we would modify this a bit, but basically this is what the but what was done as part of a bachelor's thesis that we had around this. Yeah, and the mutual attestation exchange was just based on the TLS attestation draft, and that it says that you have these like two attestation flows in both directions, and then just combined here. That well, a pretty ordinary thing. You take the TLS attestation. And there's a bit more like other variants we were actually experimenting with some flows like the platform and so forth. So, those we haven't implemented yet. Yeah, I don't know what really would do.
So maybe you can actually go back a little. You can actually see how we are trying to combine the pre-shaded keys, and also we are sending the certificate message. So that would be very nice to verify with you all whether this is seek behavior or we should actually like modify this. And also in mutual attestation case, is it possible to, for example, do things in parallel? So for example, verifying already on one side and the other side as well. So like how, when these like client and server, they are exchanging the results, for example, and when they are actually doing things. So can they do things in parallel or do they do things sequential? Because we did it sequential, but it's cost. So
Cost. How much does it cost?
I've
seen the number.
We have some numbers here.
Yeah.
Yes, so these are actually partly synthetic.
Yeah.
So on the right side, it's measured numbers where we have added, which we have added numbers, but not S&P at the station.
It's a bit unfair in the sense that this is like, certificate based stuff from a crypto perspective rather than, just pure this case. So
Yes.
of course it's nodes.
Yeah.
But yeah. I was expecting slightly worse, but it's still. But this is, as you say, synthetic, so we should take it with a pinch of salt.
Yeah, so basically the overheads of what we are doing in the protocol, you can see on the line. But it's actually quite small. But we are not doing any like generation or verification at all. We took it then later and added, and you can see that on the right side. And you can see how significantly worse it is.
Yeah. It's a nice breakdown, very, very cool. Generate evidence is what's the term?
With these particular numbers, but as mentioned, this is a bit, partly made up, and some of the signature verification numbers are actually completely made up based on what they could be.
I mean, from a performance perspective, I guess background check is definitely not great, right? You prefer, or maybe you pay the cost the first time you have to run it, and then you cache the attestation result or something at the end, and then only pay the cost for verification. I guess if you go back to your diagram, you can probably do the verifications in parallel if you can, like you don't send the finished message, you only send that after you verify it on the client side. And you send the certificate immediately, your certificate verified. And then the verifications at least can happen in parallel, I guess. But yeah.
Yeah, there's a finish here that doesn't compute because it's too early, isn't it?
It's not necessarily too early, but you can wait until you.
No, but server to client, this is not doing mutual, or is it? I don't know.
No, this is not, it's not the other one.
Because the finish is.
Well, here, okay, sorry, I'm because of I'm sorry, we have so many of these languages. I think this was the normal.
Yeah, this one, this is the this is the mutual, yes.
Yeah. So
Why does the verification request happens after the connection on the server side?
Because that's when you get the certificates, so the evidence from the clients. So you have a verification request for the client's evidence on server side.
Ah, okay, so the certificate verified finished.
Yeah.
You cannot finish there, right? You need to finish after you have verified the thing that you requested to time. But yeah, I think you can suggest this one.
Yeah, as mentioned, there could be now off the top of my head, I don't remember if it was more detailed now that we're the
That's actually what we implemented. We haven't said that like we implemented it right. So like, yeah, if you have to actually like send the finish message after the verification, they can actually call something. Yeah. Because in theory, we would like to send also data quite as early as possible. And if we are, for example, just waiting for the verification and caching the data, then it might be okay for us. But we can do it if like, the finish message is not sent.
So just to get my understanding right, so what you are saying is that this diagram might not correspond to the implementation.
No,
Is this
that diagram is as the implementation. Yes,
okay? So this is exactly
not
as per.
necessarily. It has to be right implementation of the draft.
Ah, okay, okay.
Yeah, because
But this exactly
that was our
corresponds to-
interpretation of the draft and not necessarily the best one. So
Okay, so this might not correspond to the draft, that's what you are saying, but this exactly corresponds to the implementation that makes sense. Okay, okay, right.
Like the very first prototype implementation.
Yeah,
is
it's-
Implementation is the one that in the thesis, right?
Yeah.
Okay.
The better part.
So maybe we can find this diagram in the thesis as well. And,
I think so.
you know, and the other
Should be
question
there.
is, because there's an implementation of this, is that implementation available publicly or?
No, unfortunately.
No.
An internal prototype.
For the spec, we need to think about how to support this PSK handsets, because at least I understand that if you're using the PSK TLS, then you don't send these certificate messages.
Normally, you don't.
Yeah.
Yeah, that's, but, yeah, as I read this TLS one, the basic spec, it doesn't necessarily like, said you can't do it, but I don't know.
Yeah, it's not like completely clear, but it could be that many implementations don't allow this certificate message when you're using the PSK.
Yeah.
So you can't implement the draft on top of those implementations.
But well, here since we implemented both the PSK part and the attestation ourselves, since neither of them. We did the way we wanted.
I think something else that we need to, that we can maybe do to improve this, maybe quite a bit, is the fact that, say you have the resolve evidence on the, say on the client side. Maybe there's a way to make that parallelizable with the server side, so you can compute both evidence at the same time. So if you know that the client knows that it needs to compute, generate evidence, then maybe it can do that before it gets the certificate from the server. So as long as it relies only on.
But
Sorry.
sorry to interrupt you, but like we are also asking what format we should generate. And for that, we need to actually wait from the server.
Oh, but yeah, but you can send the extensions, the encrypted extensions first, right? You can communicate what the server chooses, and then with that information, you can start computing on both sides. And the client doesn't have to wait until the server generates its evidence to start generating something.
Right, yeah.
We actually consider that this is just background check, but if the client knows that they will actually use the mutual attestation, they can actually like use password check. So like the combination when client is using password model and the server background check, that would be actually
Oh, yeah.
maybe faster.
Yeah.
Yeah, so some notes about the different options of course, different companies.
Yeah, there are options also to remember what, if you know that you're going to connect always to the guy, you can pin some of the parameters already somehow and resume with those parameters, like all the negotiation things. And so you know that this guy is gonna give me its evidence, specific profile, so I can prearrange stuff. But you need to baptize the thing once, right? So you need to hit the other guy and know what is capable of. There might be, like, for example, there are ways to cache information about latency and bandwidth characteristics of the link. Which are so crazy, but they exist. Maybe a similar mechanism could be done here to cache the pre-negotiated stuff, previously negotiated stuff.
Yeah. So we have a command line demo. I don't know if there's a much running.
Bill's just a log, so like I don't see it, but it'll be live, so who knows?
Just a quick point of order that now segments didn't have a heading in the notes in the minutes. So I took the liberty of adding it and describing it while that was taking place. So it is there.
Thanks very much.
And I think the next section is yours. Is that correct? I'm happy to note take for that section as well.
Thanks.
Sure. Yeah. So this we have actually those are two physical machines with a link of I don't know, like 1 meter long copper between them. So like that's why our numbers were pretty fast. And this server is capable of taking mutual attestation, and it's actually we try to design our solution in a way that like when the client comes and offers to have the mutual attestation, server can actually choose whether it wants to do it or not. So client now can actually like ask for mutual attestation, and here we can actually like see the log. Yeah, I don't know whether you can actually like recognize something in it. We try to also see how much time these steps are taking. So somewhere you can want numbers, how long these steps actually took us. Or the client can actually take also just a normal station. And in that case, so from this, there's a new connection, and server is just replying normally because the client is actually not supporting the mutual attestation. That's all.
Plans of sharing the code in the future, or something that you're thinking about, or you just
Thinking about it, yes, but whether it will happen,
Yeah.
we got to. Sometimes it's possible, sometimes it's difficult.
Thank you. Questions?
The way you continue on this.
Okay, so I'll try to be quick on this. Just wanted to give an overview of our prototype that I think a few people have already talked about in their presentations. I just give an overview and where we plan to go from our current place. Just to kick off with the traditional RADS diagram. Obviously, we started with this diagram in mind, and then we tried to create a link between the tester and the relying party to allow them to interact with TLS through the mediation of the verifier. Obviously, if we wanted to actually have a crystallized form for our draft, then we needed to do some work to actually get all these components talking to each other somehow. And yeah, this prototype is essentially a crystallization of those components, and not all of the ones that are represented in this diagram are here. So, for example, the ones on the upper side are not present independently, but they're included essentially as part of some other components, and we'll dig into that in a bit. But first, let me touch upon some of the points. So we wanted to have a quite comprehensive design. So for example, we wanted both peers in the TLS and TLS to be able to use attestation to authenticate themselves. That means that they can use either independently or mutually to attest each other. And they should be able to use any root of trust to attest themselves. We wanted to allow both attestation evidence and results to be used as credentials, meaning both background check and passport mode. We wanted the credentials to be used either alongside PKX, so either alongside certificates as an extension to the certificate message, or completely replacing certificates and just going with the attestation credentials. And now if we add support for PSK, then this is another direction we can be flexible in. But obviously this creates an explosion of options and configurations that you can configure a system to run, and this is fairly costly to implement and support all of them at the same time. So we chose to be a bit cheaper and only configure one specific use case, one specific configuration of the whole system. And that case is presented here. So we have essentially a Docker environment where we simulate all this, so everything runs on one machine. And in that environment, you have a client, server, and the verifier. The client is, in our case, the attester, and the server, the relying party. And we're doing background checks. So the server talks with the verifier to actually check that the client is provided good evidence. They're all connected over a prototype network. And I will be looking a bit deeper into each of these components to what we have to implement for each of them. So starting with the client, the tester. So the container that we're using, so we're using PPM 2.0 as the base root of trust. We're using a software version, obviously, since we're trying to spin this easily anywhere. On top of this software TPM, we're using Parsec to provide an abstraction for the attestation. And on top of that, we have embed TLS. So embed TLS communicates with Parsec, who gets the attestation evidence and handles all the cryptography for the actual TLS implementation. And then the TLS implementation obviously goes and talks to the server. And we've had to make changes to the parsing service and to embed TLS to make all of this work together. The parsing service is written in Rust. And actually the client piece that sits within embed TLS is written in Rust. Just that it has an FFI wrapper that allows embed TLS, which is written in C, to communicate with it. Yeah, so that's the clients. On the server side, we have again embed TLS, and in this case, we have another. I think it's another piece that's implemented in Rust, but then it's wrapped in a C FFI, which can be called from embed TLS. So embed TLS talks to the client, and then the Verizon client, which is written in Rust, talks to the verifier. And I think for this, we've had to essentially write the whole Verizon client from scratch and integrate it into embed TLS. And actually, I think as VM was mentioning earlier, the two sides of embed TLS are actually at the moment separate. So there's a different fork for the client and the server integrating these two components. But we did some more for VM's integration to actually bring them together and have them supported in the same stack at the same time. Then on the verifier side, it's actually quite vanilla deployment of Verizon. And in this case, we actually have 3 different Docker containers that run, and they have an internal Verizon internal network that they connect to. So there's a provisioning node, there's a trusted services node that provides services to the other 2, and there's a verification input. And then the verification and provisioning connects to the prototype network, and then the server and the client can connect to it that way. Now, some problems and limitations that we've had. So first of all, the build process for the container images has a history of blowing up sometimes, and I think currently it would blow up on the listener side, and we need to fix this. And this tends to happen because we didn't initially pin all the components and all the compilers and everything down to specific versions, and then as things moved on, some stuff got left behind, and yeah, things would blow up, and you wouldn't be able to actually build it from scratch. Some of the Verizon interfaces have been shifting on the E4P, but I think those are now pinned, so hopefully that should work without any hitches. The embed TLS server also currently relies on a certificate that has expired, so we need to refresh it. On the actual implementation of the of the draft, so negotiation isn't actually properly supported. It uses hard-coded types, hard-coded evidence types that are carried between. So there's no communication, for example, with the verifier to check what it supports, or communication with the root of trust to verify what it can produce. Some of the features are not supported, as I was mentioning earlier. So, for example, passport model, we didn't do that yet. And we have no benchmarking framework. And given that our root of trust is essentially software emulation of the TPM, I'm not exactly sure how relevant those benchmarking features would be, because it doesn't really represent proper root of trust. And obviously we don't really have yet support for other roots of trust. In terms of plans for the future, so we want to add support for more roots of trust, for example, CCA, even if that's in a later form for now. We want to get some benchmarking figures, but as I mentioned earlier, we need to figure out exactly what that means and what kind of root of trust we want to get those for. We want to hopefully use different TLS stacks for client server, so maybe using something like Brussels or OpenSSL on either client or server. When hopefully we can upstream some of the patches that we've made to actually get this support into upstream reports. Yeah, and if anyone wants to look at the proof of concepts, QR codes. Yeah.
I have a quick Brussels question. I'm not actually familiar with Brussels. Is it actually a Rust native sort of ground up TLS stack? It's not like a Rust presentation or.
It's a representation of an assembly implementation, but
Oh, well, it is, yeah, right, yes, okay. Yeah.
it's Rust. Or at least like, I think, sorry, you've worked a lot more with Brussels, and I'm guessing it's as native as it gets with Rust. Yeah.
Yes.
Right, okay, yeah. I mean, if we're interested in, you know, multiple TLS stacks, and Russell's maybe be one of them. As a kind of tangent, it might be interesting to look at Brussels and Parsec, right? Because I mean, at the moment, our Parsec integration is on the attester side. So if we were to look at possibly having Brussels on the attester side and doing Parsec integration there, because it might actually just be quite interesting to see what the extension points are in Brussels for, say, contracting out the signature generation to like hardware security piece, because that's what Parsec is for. So
Yeah, I don't know if Brussels already has support for backends like PPMs and stuff like that.
yeah, well, OpenSSL of course has its engines and plugins and providers and so forth. It'd be interesting to see if Brussels has a similar kind of contracted out mechanism. It might actually be a good general open source thing to look at Parsec.
Either Parsec or the ConfigTSM stuff.
Which one is that?
ConfigTSM, the new interface for the PE based.
Although that's only for confidential PMs, right? So
Yes, correct, but it's not still.
any.
Yeah, but Parsec also doesn't have support for on that side.
Maybe this is super premature, but this discussion here has triggered a few thoughts about creating an automated interop environment where we can say take the OpenSSL client and match it with an embedded TLS server on a set of things like negotiate this, negotiate that, to passport, so that we can upload, this thing would say proof from whatever the stacks are, and automatically make sure that the interop matrix is green, and when it's not green, it's reported correctly to the stack owner.
Right.
That this is futuristic stuff.
Yeah. Well, although it's interesting that I mean, we've been hearing about one lab this week, and one lab is doing some of that kind of stuff. It's not so much about I think it's more about hardware, right? And compatibility of hardware and firmware, but who knows? I mean, it might, but it does have exactly that kind of red light, green light. This works with that matrix, sort of model with CI processes built into it. So it's not a million miles away from what you're suggesting.
Yeah. I hadn't thought about this. I was thinking about watching up there.
Oh well, okay, yes.
But,
Who knows? Maybe I'm
I
sure.
should talk to the folks there, trying to understand what kind of contract that we need to have with them, in the sense of what should they ship?
Yeah, I think at the moment one lab is sort of You know, I think the rows are devices and the columns are
Yeah.
OS distros, you know, this boots, you know, these all work and run client suites and stuff. So I think if you were to add, does this talk to this via attested TLS, you're probably adding about 4 more axes to what is currently a 2-dimensional matrix, and I think it, you know, maybe that just becomes unwieldy. But so yeah, maybe it's a separate, maybe it's a separate thing.
Yeah, maybe a small comment on like benchmarking and with TPMs and like visualized and not visualized. I think as long as you know what the actual timings all are, like swapping that out shouldn't be that of an issue because most of the operations are just pretty consistent in the timing. So
Yeah. Makes sense.
yeah, if you just run a VT, just measure it pretty much once and then just use for like continuous integration and VTPM, and then we can somewhat guess like the real world numbers always from there. But of course, like VTPFs or like also with ARM-CCA, just running it in an emulator is for testing way easier than trying to find components with real hardware.
So what is the constant in the variable parts?
I mean, like if we using TPM, we have are you sending the PCRs or just the quote?
Just the code, I think.
Yeah, then you have like the key generation at one point, which is depending if you're using ECC or RSA keys. ECC is generally really fast, RSA is really slow on real TPMs compared to software. And then the quote should be quite constant because yeah, you have key generation signing and getting it out. So that is, I think was like normally around 200 milliseconds, depending on the TPM. So yeah,
I guess that's hardware TPM.
yeah, that's a hardware, like a physical hardware TPM, not like a firmware kind of thing. So
Yeah, I guess it's where, yeah, doing essentially the same.
Starting capturing the figures and then making the
Yeah.
adaptation on the fly.
Makes sense.
Thanks, John. Next.
If you are.
Where is my?
Somebody wants to take over note taking, I've just I minuted the previous 2 sections. Any volunteers to minute this section? Okay. Thanks.
True. Standardization backup. So where we are, the draft is still an individual internet draft. It's been in the working for a while. That started in July 2022, and so it's roughly 2 years, right? We're working on this. Last published version is 06, which attended just before ITF 119 March. We tend to the cadence of publication tend to be aligned with ITF meetings that have a specific cutoff date for draft submission. So it sort of gives us the right level of anxiety, right, to get the job done. For a few iterations, there was a parallel effort done by Actu that we think has been we incorporated all these requirements, and since version 05, the two branches should be now aligned, and that was factor join us over. So what we want to get in the long term is adoption in the TLS working group and getting this published ideally with a proposed standard status, which give us solid ground based on the implementation. So, there are other ways that this could end up. Say, for example, the TLS working group doesn't accept the work and reasons, and then we should probably go with the independent stream editor. Which would result in a informational status, full standard. Or if the TLS working group decides that this is not yet mature enough for the full standard status, they could send us to the experimental track. So we can have this published as experimental, and then basically the experiment is that you try it out in the field, and after a while go back to the working group to report what is the result of experimentation, and maybe they upgrade the status to standard. So there are different options here. Ideally, the quicker we get to the full standard, the better, but you never know.
Or almost can you cross that to share the screen?
So. Sorry, yeah, even though I was on sharing this. It's also confusing. So, TLS adoption criteria. So the working group wants to, the adoption in the ITF is a process, and the TLS working group has decided very recently to raise the bar for major extension. I think Usama already mentioned that the fact that major extension to the protocol and this TLS will be one need for notification. Luckily, we have Usama in the group, so we're covered from that perspective. The other thing is that you need to have interoperable implementations, at least two, but we may have three, depending on how things evolve. So that's good. In that sense, maybe having a formal way to represent the interop metrics would be great. So you might want to start thinking about how to get there. And then we need a motivated pool of editors because going through the standard process is a long way, right? It's something that you need to commit for at least 2 or 3 years. It's a PhD thesis, like it's fun. So, you need to have a consistent pool of editors that are there for all the time that needs to be. It is necessary to bring this to the thing, and you need to have TLS expertise, ITF process expertise, but that a requirement in the sense that you can get that on the job. So it's something that's as I said, the time span is so long that you need to learn a lot of things and